Hi guys, this is Dr. G here, and in this particular video I will give you a brief introduction to organic chemistry, and also we will talk about carbon hybridization in more detail. So in organic chemistry, okay, we are specifically going to talk about the chemistry of carbon. Uh, Unlike inorganic chemistry, where we are going to talk about, we learn almost all the elements in periodic table. Organic chemistry will primarily focus on carbon. And in organic compounds, primary atoms that you will see are of course carbon and hydrogen. So in organic chemistry, the two primary atoms that you are going to see are called carbon and hydrogen. And then sometimes you might also see certain atoms such as oxygen. Okay, it is very common in organic compounds, and nitrogen. Okay, these two are extremely common in organic compounds, and also halogens. Okay, halogens are actually group 7a elements. Okay, so when it comes to halogens, atoms like chlorine, bromine, fluorine and iodine, they are extremely common in organic compounds. So basically in organic compounds you are primarily going to focus on carbon and hydrogen, but sometimes you may also see atoms like oxygen, nitrogen, halogens, or even sulfur and phosphorus. And very rarely you might even see metal ions. Okay, very rarely you might even see metal ions in organic compounds. So these are the primary and secondary atoms of organic compounds, and as you can see, all of these atoms are non-metals, right? All of these atoms are non-metals. So basically, non-metals, if you only have non-metals in a chemical compound, they tend to have covalent bonds, right? They tend to have covalent bonds. That is important to remember. Okay, they are going to have covalent bonds because you're going to have bonds between non-metals. So the difference between covalent bonds and ionic bonds is that in covalent bonds you share electrons between atoms, right? So atoms share electrons between them, and then in ionic bonds there is a complete electron transfer. Okay, so in organic compounds you are always going to see covalent bonds. Okay, why? Because all the atoms that are involved are going to be non-metals. All the atoms that are going to be involved are non-metals. So you are going to see covalent bonds, or in other words, the bonds that are seen in organic compounds are formed due to sharing of electrons. Okay, so let's talk a little bit more about carbon and hydrogen, because these are the two most important atoms in organic chemistry. They are going to be everywhere in organic compounds. Okay, so when we talk more about carbons, we know that it is in group 4a. And also it is in the second period. And if you take a look at the atomic number for carbon, the atomic number for carbon is 6. Okay, that means carbon has what? Carbon has 6 electrons, 6 total electrons. Okay, carbon has 6 total electrons, and the electron configuration, of course, can be written like this: 1s2, 2s2, and 2p2. Okay, so as you can see, 2 plus 2 plus 2 adds up to 6 electrons, and of course it is in the second period. Okay, so you are going to have two electron shells. So this will be the first electron shell, and this right here is your second electron shell. And carbon has two electron shells, and the first electron shell has 2 electrons. Okay, and the second electron shell has 4 electrons. Okay, the first electron shell has 2 electrons. The second electron shell, or the outermost electron shell, okay, the second electron shell or the outermost electron shell has 4 electrons. And this outermost electron shell is also known as the valence shell. Okay, the valence shell. Okay, so this second electron shell is also known as the valence shell, and it has 4 valence electrons. So of course we know that carbon is a representative element. How do we know that? Because you have a letter A next to the group number. letter A next to the group number. So carbon is a representative element. Okay, these are general chemistry knowledge. Okay, so carbon is a representative element, and of course in representative elements the group number, which is 4 in this case, the group number is equal to the number of valence electrons. Okay, group number is equal to the number of valence electrons. So of course carbon group number is 4 and therefore it has 4 valence electrons. Carbon group number is 4, so therefore it has 4 valence electrons. Okay, 4 valence electrons. Why is these valence electrons are important? Because valence electrons are the outermost electrons. Okay, they are the furthermost electrons to the nucleus of the atom. So when you are further away from the nucleus, you are more likely to get into trouble. Okay, in other words, in chemistry, the outermost electrons are the electrons that will cause trouble, or in other words, they will get involved in chemical reactions. So basically carbon has 4 valence electrons. 4 valence electrons. Okay, so you know how to put valence electrons around the atom, right? So you will start putting one valence electron at a time around the 4 sides of the atom, okay, or the element symbol. And then if you have, let's say, 5, then you will start pairing. Okay, you will start pairing. If you have 6, it will be like this, 7, 8. Okay, so that is how you put valence electrons. But of course carbon only has 4 valence electrons. So the Lewis structure for carbon will be like this. You have 4 valence electrons, and then each of them are unpaired, and they will be situated like this around carbon. Okay, so this is the Lewis structure for carbon. Okay, so if someone asks you to draw the Lewis structure for nitrogen, okay, let's say someone asks you to draw the Lewis structure for nitrogen, you look at the periodic table and you figure out the group number, which is group 5A. Okay, which means the number of valence electrons is equal to 5. So nitrogen has 5 valence electrons, right? Which means nitrogen has 5 electrons in the outermost electron shell, so they are important in chemical reactions. So in Lewis structure we have to put those 5 electrons around nitrogen. So you will put like this: 1, 2, 3, 4. The first 4 electrons will always be on the 4 sides. Okay, 1 electron each per side, and then after 4 electrons you will start pairing. Okay, so for nitrogen you have 3 unpaired electrons and then 1 lone pair. For carbon you have 4 unpaired electrons. Okay, so these paired electrons are known as lone pairs. Okay, they're known as lone pairs. And then the other single electrons, okay, we call them unpaired electrons. So in general chemistry lectures, I mentioned that electrons can be considered as people, right? Yeah, because I mean, pairing is like getting married. Okay, so if you are married, if you are an electron and if you are married, you are more stable. But if you have unpaired electrons, you are unstable, or in other words, you are always looking to pair up. If you have unpaired electrons, you are always trying to pair up, so you always have to find a nice partner to settle down. So you are unstable. So when atoms have unpaired electrons, they will always try to pair up. Okay, so let's say carbon has 4 unpaired electrons, and carbon will always try to find another electron. Let's say this X is from another atom, let's call it Y. Okay, and then now these unpaired electrons are paired, okay, by sharing electrons between carbon and Y. Okay, that is another atom, and they are more stable. So for carbon you have 4 unpaired electrons, which means it needs to find 4 other unpaired electrons. Carbon needs to find 4 other unpaired electrons so that it can pair up all the unpaired electrons. Okay, so if carbon can find 4 other unpaired electrons, then it can pair up, and then make 4 bonds, right? So these paired electrons, we call them bonds. These paired electrons are also known as bonds, right? So you remember from bonding chapter, okay, when you pair up these unpaired electrons, these paired electrons are considered to be bonds. So carbon can form a maximum of how many bonds? Carbon can form a maximum of 4 bonds. Carbon can form a maximum of 4 bonds. Okay, so that is important to remember. Okay, so when we talk about chemistry of carbons and then the structure of carbon compounds, okay, you will always try to put 4 bonds on carbon. Okay, what do you try to do? You will always try to give 4 bonds to carbon. That is an important thing to remember. You will always try to give 4 bonds to carbon. Why? Because carbon has 4 unpaired electrons. So unpaired electrons are not stable. So they will always try to obtain 4 other unpaired electrons and then try to pair up. So if you do that, you get 4 bonds. Okay, each paired electron pair is known as a bond. Okay, each paired electron pair is known as a bond. Or in other words, okay, carbon has 4 unpaired electrons, right? Unpaired electrons. So the number of unpaired electrons is equal to the number of bonds. Okay, number of unpaired electrons is equal to the number of bonds. Or in other words, why do we need to pair up these electrons? Because you want to achieve an electron octet. Okay, remember the octet rule. Okay, so in organic chemistry we are just glancing through these. Okay, glancing through these things that we learned before. So remember the octet rule. Okay, which means the atoms will try to have 8 valence electrons in the valence band, right? So that is called octet rule. Or in other words, these noble gases, okay, noble gases have, okay, let's say X is a noble gas. Noble gases always have 8 valence electrons. Okay, so they are very stable. That is why we call them noble gases, right? So if carbon wants to reach the electron configuration of the noble gases, then it needs 8 electrons, right? It needs 8 electrons. So how do you get to 8 electrons? So you already have 4, you have to add 4. Okay, that is how you get to 8. So if you are adding 4, that means you need 4 bonds. Okay, so if you're adding 4, you need 4 bonds. All right, so basically the take home message, if you just, let's say, you took general chemistry like 2 years ago and you don't remember anything about general chemistry, if you want to be successful in organic chemistry, this is all you need to know. Okay, so carbon is in group 4a, which means it has 4 valence electrons. Okay, in order to obtain the octet rule, or in order to achieve the noble gas configuration, okay, carbon needs to pair up its 4 unpaired electrons in the valence band. That means it needs 4 bonds. Okay, so carbon will almost always try to achieve 4 bonds. Carbon will always, or almost always, there are a couple of exceptions, of course, but most of the times, 99% of the times, carbon will always try to obtain 4 bonds. Okay, that is important to remember. All right, so how about hydrogen? Let's talk about hydrogen. I mean, hydrogen has an atomic number of 1, right? So that means it has only 1 electron. The electron configuration is oneness. So hydrogen will try to achieve the noble gas configuration of helium. Okay, helium is unlike other noble gases. Okay, helium does not have 8 electrons. So helium only has 2 electrons. Okay, helium only has 2 electrons. So if you are hydrogen, you try to achieve the helium noble gas configuration, because it is the closest noble gas to hydrogen, right? So when you are trying to achieve the helium configuration, you only need to find one other electron. You only need to find one single unpaired electron. So all you need to do is to make a single bond. So if you are hydrogen, okay, if you are hydrogen, your whole purpose is to try and pair up your unpaired electron. So your whole purpose is to pair up your unpaired electron by finding another atom, with one other electron, one other unpaired electron. Okay, so hydrogen will always form a single bond. The hydrogen will always form a single bond. No double bonds, okay, just a single bond. That is all it needs to achieve the noble gas configuration of helium. Okay, so let's say for carbon, what did we learn now? So if you have a carbon atom, it will always try to form 4 bonds. Why? Because in order to achieve the noble gas configuration, it needs to form 4 bonds. In order to achieve the noble gas configuration of helium, hydrogen needs to form a single bond. Okay, a single bond. So if you only have one carbon atom, let's say as an example, you have one carbon atom, okay, which means this carbon needs 4 bonds. How many hydrogens will you need to form a molecule between carbon and hydrogen? How many hydrogens atoms, or how many hydrogen atoms you will need to form a molecule between that carbon and hydrogen? All right, so carbon needs 4 bonds. We know that carbon needs 4 bonds, 4 single bonds, and then hydrogen need only 1 bond. Okay, so hydrogen can only occupy one of the carbon hydrogen bonds, right? So you basically need 4 hydrogen atoms. To make a molecule between one carbon atom and hydrogens. Okay, so that is how it looks like. So this is the most important thing to remember. Okay, how many bonds carbon will need, how many bonds hydrogen will need. So in organic chemistry, the basic thing that we will learn is to connect carbons and hydrogens, and of course carbons and carbons. Okay, in organic chemistry, the most important thing to do is to connect carbon atoms and sometimes connect carbon and hydrogen atoms. Okay, so we are going to learn how to connect carbon atoms, and then of course connecting carbon hydrogen atoms is only one way, right? You take one carbon and then you connect it to a hydrogen. Okay, that is the only thing that you can do. But when it comes to carbon, okay, of course carbon can have 4 bonds. Okay, so you can connect two carbons using a single bond, or sometimes you can connect two carbons using a double bond. Okay, you can connect two carbons using a double bond. Okay, and sometimes there are situations where you can connect two carbons using a triple bond. There are situations where you can connect two carbons using a triple bond. So if you are connecting a carbon and a hydrogen, this is the only way that you could do it. You are making a single bond between carbon and hydrogen. If you are connecting two carbons, there are 3 different ways. Okay, you can use a single bond. You can use a single bond to connect two carbons. Okay, or you can use a double bond, or certain situations you can even use a triple bond. You can use a triple bond. All right, so let's look at the single bond in more detail. Okay, so if you are making a single bond between these two atoms, okay, these two carbon atoms, each carbon needs 4 bonds. But you're only making a single bond. So each carbon is going to need 3 other bonds, right? 3 other bonds. So here are the 3 other bonds. 1, 2, 3. 1, 2, 3. So if you're going to have a double bond between the two carbon atoms, then out of the 4 bonds, you already made 2 bonds. Okay, how many left? 2 more, right? So 1, 2. 1, 2. So if you have a triple bond between the two carbon atoms. You know, each carbon needs 4 bonds, and you already have 3 bonds, a triple bond between the two carbons. So you only need one additional bond. For each carbon, you only need one additional bond, okay? For each carbon, you only need one additional bond. So these are how carbons can connect between each other. If you are a carbon, you can connect to another carbon in three different ways. You can connect to another carbon using a single bond. So you two are only sharing 2 electrons. So if you have a single bond, the two carbons are only sharing 2 electrons between each other. Okay. You can also connect to another carbon using a double bond, which means you are sharing 2 pairs of electrons between each other. Okay. If you're making a triple bond, between another carbon, you are sharing 3 pairs of electrons between each other. Of course, dot is an electron from one carbon and a cross is an electron from the other carbon. Okay, so this carbon shared 1 electron, so it should have 3 other electrons, and this carbon shared 2, or each carbon shared 2, so they should have 2 other electrons. And then in here, you guys shared 3 electrons out of the 4, you should have 1 other electron on you. Okay, all right, so these are the methods that carbon will use to bond to different carbon atoms. The most common one is, of course, the single bond, okay, where the two carbons are connected to each other by 1 electron pair. Okay, they only share a pair of electrons. Or you can see double bonds where 2 carbon atoms share 4 electrons. Or you can even see triple bonds. Okay, so what is the difference and similarities between the 3 bonds? In order to understand the similarities and differences, we need to look at the hybridization of carbons. Okay, so we need to see how the orbitals are going to be hybridized for the carbon atoms. So for that, we are going to go to our lecture note and we will talk about more details on the hybridization of carbon. Okay, to understand these single bonds, double bonds, and triple bonds, next we will talk about the hybridization of carbon. So in this part of the video, we will first talk about the single bonds of carbon. So in other words, let's primarily focus on the carbon-hydrogen bonds, so carbon-carbon single bonds. Okay, so these carbon-carbon single bonds or carbon single bonds, okay, it could be between carbon and hydrogens, or it could be between carbon and carbons. So when you are talking about single bonds, okay, the hybridization of a carbon is going to be known as sp3 hybridization. Okay, so if a carbon has only single bonds, okay, if a carbon has only single bonds, then the hybridization is known as sp3. Okay, in here, what happens is that, of course, you know, the 4 electrons in carbon are present in s and p orbitals. Okay, so in the s orbital you have 2 electrons, in the 2s orbital you have 2 electrons, and in the 2p orbitals you have 2 electrons. But in order to make 4 single bonds, okay, and ideally these 4 bonds should be identical. Okay, so in order to make identical single bonds, carbon actually rearranges its orbitals. Okay, carbon actually rearranges its orbitals. We call it hybridization. So you know, s orbitals are like a sphere, spherical. Okay, so s orbitals are spherical, and then p orbitals look like dumbbells. Okay, so basically when it comes to 2s, it has a spherical shape. Okay, so in the s orbital you have 2 electrons, and then out of the 2p orbitals, out of the 3 2p orbitals, you actually have 2 orbitals with 1 electron, and the other orbital does not have an electron. Okay, so this is how originally the electrons are present in a carbon atom. Okay, so you have two electrons in the spherically shaped 2s orbital, and then you have one electron each in two of the three 2p orbitals. Okay, so before making any bonds, okay, I mean, carbon will not basically try and make four bonds using these four orbitals as is. Okay, it is like, let's say bonding are like, meeting someone and starting a relationship, right? So if you are meeting someone new, okay, you don't just uh, go out and meet new people with the clothes that you have at home, right? So you will put on a new outfit, you will put on a face, you will at least you know brush your teeth and then get ready, and then only you will go out and find new people, right? So if, let's say, you are carbon, so if you are carbon, you don't want to get out with these orbitals. They are not going to work. They are not similar, and then you have to have uh, awkward bonds, okay, if you are going to make bonds like using these three orbitals, okay, and the bonds that you're going to make will not be identical. Why? Because s orbital has a different shape and the p orbitals have different shapes, right? So no, if you are carbon, you need to get excited, and what happens is that first carbon will go from the ground state where you have two electrons in the 2s and two electrons in two of the 2p orbitals. From the ground state you will go to an excited state. This is where you will put on a face and then put on some new outfit, okay? So you basically take one of these electrons from 2s and you will put it into the 2p orbital. Now carbon has four unpaired electrons. As you can see, now carbon has four unpaired electrons. Initially carbon only had two unpaired electrons, okay, but now once it is excited, it has four unpaired electrons, three on the 2p orbitals and one on the 2s orbital. Okay, so if carbon make a bond like this, it will probably make four bonds, but the problem is that you will have two different bonds. S orbital will form a different bond, and then these three electrons will form three bonds that are going to be different from the s orbital. So no, still the carbon will make two different bonds if it is to make bonds out of these four electrons in the excited state. So when carbon is in the excited state, what it will do is it will try to hybridize the orbitals. In other words, it will basically blend the 2p orbitals with the 1s orbital and make hybridized orbitals. Okay, so you will basically put the three 2p orbitals and the 2s orbital, mix it, and then make a nice hybridized orbital which we call sp3. Why do we call it sp3? Because to make these hybridized orbitals, you only used one s orbital and you used three p orbitals. That is why we call it sp3. Okay, by mixing one s orbital and three p orbitals, you are going to make the sp3 hybridized orbitals. Okay, and of course, since you are mixing three p orbitals and only one s orbital, of course these sp3 hybridized orbitals will have more p character. Okay, it will have more p character. Why? Because 75% of the orbitals are actually from p. Okay, 75% of the orbitals are from p, right? So usually this will have more p character and less s character. That is why the energy of these sp3 hybridized orbitals, okay, this is energy, the energy of these sp3 hybridized orbitals are closer to p orbitals, okay, closer to p orbitals. But the good thing about these hybridizations is that all four of these hybridized orbitals are equivalent. They are equivalent, right? So these hybridized orbitals are equivalent, so you can't separate them from the shape or the sides. All of them are equivalent. So basically, when carbon is forming bonds, it will have four orbitals. It will have four orbitals that are going to be equivalent to each other. So once they are formed into a bond, you can't distinguish them. Let's say each of these four sp3 hybridized orbitals are going to bond with hydrogen atoms. All four of these bonds of these carbon hydrogen bonds will be equivalent. Okay, all 4 of these bonds will be equivalent. So in this slide I am actually showing you how these sp3 hybridized orbitals are going to form a methane molecule. Okay, so in here the other thing to remember is that these sp3 hybridized orbitals, they are a little bit asymmetric when it comes to the shape. They are unsymmetrical. So basically, I mean, you remember that p orbitals have a dumbbell shape, right? So this one is like a balloon. Okay, it has a it is asymmetric, it is not similar. Okay, the blue part and the red part, okay, they are not equal in size like the p1, okay, p orbitals. So they are asymmetrical, or you can say unsymmetrical. Okay, so they're like a balloon. Okay, so keep that in mind. All right, so when you're making 4 bonds, of course, when you put 4 orbitals in 3D space, okay, if you remember the shapes lesson that we learned in general chemistry, we learned that when you have four bonds or 4 orbitals in this case, the best way to put these 4 orbitals is in tetrahedral shape, right? So the best way to put these 4 orbitals is in the tetrahedral shape. So basically, in the tetrahedral shape, each bond or each orbital has a bond angle of 109.5. Okay, so the bond angle is around 109. Okay, and it is a very symmetric shape. Okay, so this shape is known as tetrahedral. Okay, if you don't remember tetrahedral shape, I would recommend that you guys go and take a look at your general chemistry notes, or at least listen to the video. Okay, so these sp3 hybridized carbons will always have a tetrahedral shape. Remember that sp3 hybridized carbons will always have a tetrahedral shape. And then each of these orbitals will linearly overlap with the s orbital of hydrogen. Okay, each of these sp3 hybridized orbitals of carbon will linearly overlap with the s orbital of hydrogen, and then form a single bond. Okay, a single bond which is also a sigma bond, right? And the bond length between carbon and hydrogen bonds is around 109 picometers. Okay, 109 picometers. All right, so this is how it happens. And the bond strength is around 439 kilojoules per mole. I usually don't remember these energies. Okay, so you don't have to. And the bond angle is the typical bond angle for tetrahedral shape. All right, so here's another example. In here I have the molecule called ethane. Okay, the thing about ethane is that you have 2 carbons. Okay, you have 2 carbons, and then the remaining 3 bonds of each carbon is attached to hydrogens. Okay, so you have 6 hydrogens and 2 carbons. And as you can see, okay, this is how you understand the shape of each carbon. Okay, so each carbon has only single bonds. So if each carbon has only single bonds, the hybridization of each carbon should be what? sp3. The hybridization of each carbon is sp3. Okay, that means each carbon is going to have a tetrahedral shape. And the bond angles of each carbon and hydrogen bond, or a carbon hydrogen and a carbon carbon bond, is going to be around 109 degrees. And the bond strengths are also listed here. As you can see, carbon hydrogen bonds have a higher bond strength, so it is very hard to break carbon hydrogen bonds as compared to carbon carbon bonds. Okay, but still they both have very high energies. And also when it comes to bond length, okay, carbon hydrogen bonds are around 109 picometers, and carbon carbon bonds are around 154 picometers. Okay, so as you can see, carbon carbon bonds are slightly longer than carbon hydrogen bonds. Okay, but the take home message is that if a carbon only has single bonds, the hybridization is going to be sp3. All right. Next, we are going to talk about the you can take a look at these slides later on, okay, and in more detail, of course. But next, we are going to talk about and also try this worked example at home, okay. You might want to pause the video and see if you could do it. But next, we are going to talk about sp2 hybridized orbitals, okay. So sp2 hybridized orbitals are important when carbon atoms have a double bond. Okay, so if you have a carbon atom which contains a double bond, that carbon atom has sp2 hybridized orbital. So in other words, that carbon is sp2 hybridized. Okay, so let's take a look at it. So basically, once again, the carbon will go from ground state to the excited state, okay, because you're going to make a bond. So carbon has to get excited, right? So it will have four singly occupied orbitals. It will have four singly occupied orbitals, one s orbital and three p orbitals. And then in this hybridization, as the name implies, it is sp2, right? It is sp2. That means this hybridization has one s orbital and then two p orbitals. So this one of the the s orbital that we have will hybridize with only two p orbitals, okay. We will leave one p orbital alone, okay. So here is the p orbital that is not hybridized, and then the s orbital and two of the p orbitals will hybridize and then form an sp2 orbital, sp2 hybridized orbitals, okay. So you are going to have three sp2 hybridized orbitals. Why? Because you used one s orbital and then two p orbitals, so you should get a total of three sp2 hybridized orbitals. So you have three sp2 hybridized orbitals which are capable of forming three similar bonds, and then you have a p orbital that is not hybridized, okay, that is not hybridized. So this is how the hybridization occurs. Once again, the shape of sp2 hybridized orbitals will be similar to sp3 hybridized orbitals. It will be asymmetric like a balloon, okay. We'll have a one large side and a one smaller side, and the p will have the dumbbell shape, okay. P will have the dumbbell shape. So basically in this hybridization, what happens is that the three hybridized orbitals will stay in one plane. The three hybridized orbitals will stay in one plane. So it will be like a trigonal planar shape, okay. So the three hybridized orbitals, the sp2 hybridized orbitals will stay in one plane, and the p orbital will sit perpendicular to the three sp2 hybridized orbitals, okay. I think I have a image in the next slide. Yeah, there we go. So you have, these green orbitals are the hybridized orbitals. So those three sp2 hybridized orbitals will stay in the same plane, okay, in a trigonal planar shape, and then your p orbital will be perpendicular to all three of these hybridized orbitals, okay. So when you have two carbons with the sp2 hybridization, okay, of course one of the sp2 orbitals will linearly overlap with the other sp2 orbital, and then this will form a sigma bond, okay. This will form a sigma bond, and the unhybridized p orbital of each of the carbon atoms will laterally overlap. It is not a linear overlap. Why? Because they are not overlapping face to face like the hybridized orbitals. So these two will laterally overlap, or you can say it's a partial overlap, side by side, okay. So then you will make a double bond, okay. So that will be a pi bond, okay. So p orbitals will overlap laterally and then it will form a pi bond. All these details were written in the previous slide, so you can actually go back and read that slide if you have to, okay. So basically that is how you make a double bond, okay. Out of the two bonds or the double bond that the carbon and carbon share between each other, one bond will be a sigma bond. It's a linear overlap between the hybridized orbitals. And the other bond is actually a pi bond, which is between the two p orbitals of the two carbons. Okay, and then of course the other two hybridized orbitals will form two other sigma bonds with something else. Okay, in ethylene it's with hydrogen. Okay, in ethylene or ethene it's with hydrogens. Okay, so basically here is the take home message. I mean, you can read these slides and then try to draw these structures again and then look at the bond lengths and everything, but this is the most important summary of this hybridization. Okay, so if a carbon has a double bond, that carbon has sp2 hybridization. Okay, and also the geometry of that carbon or the shape of that carbon will be trigonal planar. The geometry or the shape of that carbon will be trigonal planar. All right, so once again you can pause the video and then try to do this example. Okay, and then in a second I will post the answers. All right, so next up we are going to talk about sp hybridized orbitals. By now, I mean, you should be able to figure this one out by yourself. Okay, as the name implies, for these hybridized orbitals you are going to use one s orbital and then one p orbital, right? And you are getting a total of two sp hybridized orbitals. Okay, so here is the ground state of carbon, just like before, and then you get excited so that you know the paired electron, one of the paired electrons will be excited to a p orbital. And then for the hybridization you are using one p orbital with the s orbital, so you only get two hybridized orbitals. Okay, and then you have two unhybridized orbitals, which are p orbitals. Okay, and then when you are making bonds, okay, let's say you have two carbons that are sp hybridized. So basically the sp hybridized orbitals will basically stay linear to each other. Okay, they will stay linear to each other. So here is one sp hybridized orbital, here is the other one. Okay, they are linear to each other, and then the p orbitals will align perpendicular to each other. Okay, so all these orbitals, the p orbitals, the two p orbitals and the two sp orbitals, they are perpendicular to each other. Okay, so when you are making bonds, the first thing that will happen is that you will make a sigma bond, because they are overlapping face to face, right? So it's a sigma bond between the sp hybridized orbitals. Once you have the sigma bond, what happens is that it will also have partial overlaps between the two p orbitals. Okay, so you can actually have two pi bonds. Here is one pi bond, okay, between these two. There is one pi bond, and also here's another one. The other perpendicular one can also have a partial overlap. So basically you will have two pi bonds. Okay, two pi bonds. And for pi bonds you are using what? For pi bonds you are using p orbitals. For sigma bonds you are using sp hybridized orbitals. So basically in a carbon-carbon triple bond, okay, you will have one sigma bond which is formed between sp hybridized orbitals of the two carbons, and then you will have two pi bonds. Here is one, here is the other. You will have two pi bonds which are formed by partial overlap or lateral overlap between p orbitals of the two carbons. Okay, p orbitals of the two carbons. All right, so if this figure is messy, I would recommend that you guys try to assemble this structure using a model. Okay, but basically the take home message or the summary that you need to remember is that if a carbon has a carbon-carbon triple bond, that carbon has sp hybridization. You can close your eyes and then say that that carbon has sp hybridization. And also the bond angle between the triple bond and the single bond is 180 degrees. So therefore it will have a linear shape. The geometry of the triple bonded carbon will be linear. Okay, the geometry of the triple bonded carbon will be linear. Okay, so the triple bonds look like they're straight. Why? Because the sp hybridized orbitals will align. Okay, sp hybridized orbitals will align in a 180 degree angle. Okay, so here is a summary of the bond lengths and bond energies of single, double and triple bonds. Okay, so you can take a look at it. Okay, but the take home message is that when you compare carbon bonds, okay, carbon bonds, okay, bond lengths, if you take a look at the bond lengths for carbon bonds, okay, single bonds are the longest, and then the double bond, and then the triple bond. I mean, this is obvious. Why? Because when you have more connections between carbons, or when you have more bonds or multiple bonds between two carbons, the two carbons tend to get closer to each other. That is why triple bonds have the shortest bond length, then double bonds, and then single bonds. Okay, and if you take a look at the bond strength, okay, so as you can see, okay, let's use calories. Okay, so these are the calories that you will need. So triple bonds are the strongest, and then double bonds, and then single bonds. Okay, so single bonds are the weakest, but these numbers are misleading. Why? Because I mean, in when you are breaking a carbon bond, you only have one bond to break, right? But if you are making a carbon double bond, you are breaking two bonds. So average bond strength is actually, I mean, weaker as compared to a single bond. So you are breaking three bonds when you are breaking a triple bond, right? So if you take the average bond strength, it is actually weaker for a triple bond. Okay, all right, with that I'm going to stop this video. I think we discussed a lot about hybridizations, but here's the thing, guys. In this video, all I want you to remember are two things. If you have a carbon will almost always, or 99% of the times, try to find four other bonds. Why four other bonds? I mean, try to make four bonds, because it will try to achieve the noble gas configuration by forming four bonds. Okay, so that is something important to remember. Okay, so if you have a carbon, you will always try to give four bonds to that carbon. And then carbon can have single bonds, double bonds, or triple bonds based on the hybridization of the carbon atom. So if a carbon only has single bonds, hybridization is what? sp3. If a carbon has a double bond, it will be sp2. If a carbon has a carbon triple bond, the hybridization will be sp. And here's something to think about. If a carbon has two double bonds, okay, what would be the hybridization? The answer is sp, but think about it. Okay, all right, guys, with that I'm going to stop this video. Please let me know if you have any questions. You guys have a good one. Okay, take care.